Hello everyone, I'm Yao Li from China University. In this lecture, we are going to learn some basic knowledge about Mohr Coulomb failure criterion. Many models have been developed to evaluate shear strengths of soils, which include Mohr Coulomb, Clay, Tresca, and more. Among them, Mohr Coulomb is the simplest and by far the most popular model in research and engineering. In the Mohr Coulomb failure criterion, Mohr assumes that the failure of the material is due to shear. The shear strength is a function of the normal stress at this plane. The first figure shows the direction of the shear stress and normal stress during shear deformation. It should be noted that the function is nonlinear at large normal stress, and it is simplified as a linear function in most cases, as shown in the figure. When the shear strength at any point reaches the shear strength of the material, it fails. The two figures show the relation between shear stress and normal stress for cohesive soil such as clay and silt, and non-cohesive soil such as sand and gravel. Green dots in the figures show individual test results. When the test number is large enough, we can feed the dots with function which is a linear function in this case. In the first figure, we can see the shear stress equals sigma multiply tangent phi plus c, in which sigma is the stress applied on the vertical direction, phi is the internal friction angle, c is the cohesion. For non-cohesive soil, as shown in the second figure, the relation is simplified due to the fact that non-cohesive soil usually has no cohesion. The shear stress equals sigma multiply tangent phi. The two figures show the Mohr Coulomb failure criterion in Mohr circle. In the first figure, we have two given values, sigma 1 and sigma 3, which can be calculated from the test results. The two values give a unique circle with a diameter equal sigma 1 minus sigma 3. When the circle is within the range bounded by the equation, the soil is safe. When the circle reaches the boundary, it fails, as shown in the first figure. When sigma 1 and sigma 3 are increased and the boundary is not reached, the soil still can be safe since the shear strength of the material is not reached, as shown in the second figure. For non-cohesive soils, according to the geometry in the figure, we can easily get the sign phi as indicated in the first equation. The implication of this equation is that Mohr Coulomb failure criterion defines failure when the maximum principal effective stress ratio, called maximum effective stress obliquity, sigma 1 prime divided by sigma 3 prime is achieved, and not when the maximum shear stress is achieved. In addition, as shown in the second and third figures, knowing the friction angle and sigma 3, we can easily calculate the sigma 1. Similarly, knowing the friction angle and sigma 1, we can easily calculate the sigma 3. For cohesive soils, according to the geometry in the figure, we can easily get the sign phi as indicated in the first equation. Then the sigma 1 and sigma 3 can be calculated in given conditions. Because the cohesion indicated by C is considered in cohesive soils, corresponding equations are more complex compared with that in non-cohesive soils. It should be noted that the alpha CR is the angle between shear failure plane and the major principal stress, which equals 45 degrees plus half of the friction angle. It should be noted that the shear failure plane isn't the plane with maximum shear stress. Mohr Coulomb failure criterion can be used to evaluate the state of the soils. To check if it is failed at one point, first we need to get the stress state of the soil elements, including the normal stress in the horizontal direction, sigma x, normal stress in the vertical direction, sigma y, and shear stress in the xz plane. Then we can calculate the sigma 1 and sigma 3. After that, we can evaluate the stress state of soil element. In the first method, we can use the calculated sigma 3 to calculate its corresponding sigma 1 at failure. When the calculated sigma 1 equals the sigma 1 at failure, the soil is under critical state. When the calculated sigma 1 is smaller than the sigma 1 at failure, the soil is safe. When the calculated sigma 1 is greater than the sigma 1 at failure, the soil is under an impossible state and already failed. In the second method, we can use the calculated sigma 1 to calculate its corresponding sigma 3 at failure. When the calculated sigma 3 equals the sigma 3 at failure, the soil is under critical state. When the calculated sigma 3 is greater than the sigma 3 at failure, the soil is safe. When the calculated sigma 3 is smaller than the sigma 3 at failure, the soil is under an impossible state and already failed. In the third method, we can use the calculated sigma 1 and 3 to calculate the corresponding friction angle at a critical state. When the friction angle is greater than the friction angle at a critical state, the soil is safe. When the friction angle equals friction angle at a critical state, the soil is under critical state. When the friction angle is smaller than the friction angle at a critical state, the soil is under an impossible state and already failed. Here are all the contents in this lecture. Thanks for your listening and see you next time.